All right, how's it going, everybody? We are here on Friday, February 12th. Today, we're going to be looking at section 7.1, inverse trig functions. In particular, we're going to be looking at the inverse functions for sine, cosine, and tangent today. And so, as we're now transitioning into chapter 7, right, we spent the first chunk of the semester on chapter 6 learning about our trig functions. And all we've really done so far is we've evaluated trig functions, right? That was all what chapter 6 is about, is defining trig functions and understanding how to evaluate them in any given context. The reason that we want to really be able to do this is so that we can understand trigonometric identities, which we'll see in chapter 7, and trig equations is one of our big topics here in chapter 7. So I just kind of want to highlight that difference a little bit right here. And we'll be using lots of our information from section 5.4 in the previous video about inverses today to help us define the inverse trig functions that we will want. Our last example that we'll look at today will be one of our trig equations that we want to be able to solve over the course of this chapter here. We've got a couple other components we want to build up along the way. So first, I just want to kind of highlight this distinction between an expression and an equation. I think that this is a thing where when we stop and think about it, we know it, but let's stop and kind of see what the difference is between the things that we've done. In algebra, you might be evaluating an expression. This is an expression. There is no equal sign here. This is just a quantity. Down here, we see equal signs, which means this is a relationship between two quantities, the relationship being they are the same. So kind of identify that difference right here. Here, if I were evaluating this expression, I can follow my order of operations to simplify some quantities here. And we could evaluate that expression to be 29, right? That's something that we might see in an algebra class. What we've been doing here in chapter 6 is evaluating expressions that contain trigonometric quantities. So we do things like saying, I know how to evaluate the sine of pi fourths now. I know that my pi fourths guy is going to be the 45-degree angle, so our sine and cosine amounts are the same. That's going to be my root 2 over 2. We've seen things like cosine of pi sixths. I know that cosine is my horizontal amount. I can see with pi sixth or 30 degrees, the horizontal amount is more than the vertical amount. So that should be my root 3 over 2. And that's being squared here. So I'm going to get the square root of 2, because those 2's were canceling right there, minus, it looks like this is going to be 3/4. I don't have any cleaner way to represent this right here since I can't combine a square root with non-square root terms right there. So that's going to be a good final answer for evaluating that trigonometric expression. Our goal moving into chapter 7 now is to solve trigonometric equations. So this is more stuff that you've seen from algebra right here, that we could solve this equation for x. This is a relationship saying if 3 plus 2x is the same as 11, what value is x? Well, I could subtract 3 from both sides of the equation to get 8 and divide both sides by 2 to get that x must be 4 for these two sides to be equal to one another. Excuse me. And similarly here, our goal is going to be able to say we want to be able to solve for x, just like we solved for x over here. So I can kind of get started on this guy right here. I can subtract 1 from both sides. And I can divide both sides by 2. But now we kind of have to say to ourselves, what are we doing here now? Well, kind of what we learned in the last class is that every time that we are performing any of these operations here, every single step that I've done in both of these equations settings right here has been applying an inverse operation. The inverse of addition of 3 is subtraction of 3. I applied the inverse operation of subtract 3 to both sides to undo the addition of 3 on the left. Then we had multiplication by 2. I used the inverse operation of division by 2 to eliminate the 2 from this side, but I had to divide the other side by 2 as well. Same thing over here. We had addition of 1 as an operation. The inverse operation is subtraction of 1. That's what I performed on both sides. We had a multiplication by 2. I performed the inverse operation of division by 2 on both sides to eliminate that. Finally, our last step should be, I've got another sneeze here, should be that we have the sine of x. So it should be that what we want to do is apply the sine inverse function to both sides so that the sine of the sine inverse cancels, just like multiplication by 2 and division by 2 cancel, just like addition of 1 and subtraction of 1 cancel, to land at something that seems like sine inverse of 0.25. But the point is that, like, I don't really know how to interpret that quantity, right? That's kind of a Like that's going to be the algebraic maneuver, just like you divide by 2 to undo multiplication by 2. That's an inverse operation. I'm going to use the inverse sine function to undo the sine function to solve for x. But we kind of need to just like ask the question like how should sine inverse of a function be, like sine inverse of a value be defined? We need to kind of pin that down here today. So our goal for today is kind of try and understand this quantity a little bit better right here. So what we saw in our previous video was that we looked pretty closely at this y equals x squared function at the end of the video, and we determined that y equals x squared is a 2-to-1 function, meaning there are 2 inputs associated with every 1 output. If I said to you I squared a number and I got 4, then 4 is the output from squaring. However, what you know is that there's 2 different numbers that we could have squared to get 4. We could have squared positive 2 or negative 2. So when I'm asking you this inverse question now, if I know that my output was 4, and I said, what did I square? There's 2 possible answers. That means that it's not a function. Everything that's a function, you give 1 input, there's 1 associated output. So what we had to do is we had to say, listen, since the y equals x squared function is a 2-to-1 function, we need to restrict the domain of y equals x squared to a domain over which it is only 1-to-1. We determined that only looking at the positive numbers would do that for us, right? Just the right-hand side of the parabola right there means there's only 1 possible output for each of these guys. Then I say, hey man, I squared a number and got 4. What did I get? Your only option is to give an answer in the 0 to infinity interval, which would be 2. 2 is the number that we square to get 4 in that interval. So by restricting the domain of y equals x squared from infinity to only 0 to infinity, that made it 1-to-1. And because it was 1-to-1, we were then able to identify the inverse function as the square root function. And because we're saying that the inputs of the y equals x squared function were reduced down to 0 to infinity, that means that the outputs of the inverse function must also be spanning from 0 to infinity, right? So since we can only plug in the x values in 0 to infinity into the restricted domain function, we're only going to get out y values from 0 to infinity because that's exactly what inverses do. They swap the role of inputs and outputs. So we want to do this exact action, but we want to perform this on sine, cosine, and tangent for today, the thing that we talked about for y equals x squared in the previous video. So we know that the graph of y equals sine of x is infinity to 1, meaning if I'm saying to you, hey, listen, I got out the value of 1 from the sine function, well, that could happen at pi halves. That could also happen at 5 pi halves, 9 pi halves, 13 pi halves, and we could just keep on going. There's an infinite number of values that it could have been that we took the sine of to get 1. That's not going to work for me for the inverse because then that would mean that the inverse isn't a function. There's an infinite number of possible outputs for every input. What good was that to us right there, right? So what we want to do is we want to restrict the domain of the sine function, which currently is negative infinity to infinity. You can plug in anything you want into the sine function. We need to choose a narrow range of values over which all the outputs are only achieved 1 time so that it is a 1-to-1 function. There's only 1 input for each output, or 1 output for each input over the values that are in that interval. So it's going to help us to look at a graph of this guy to do this. And our issue is that there's going to be an infinite number of choices because this function just repeats its behavior an infinite number of times. But a good piece of guidance for like all of math forever is we really like the number 0. It should be your favorite number to do math with. It makes everything as easy as possible. So out of all the choices that we have, let's go ahead and pick whatever interval has the number 0 in it to kind of make our lives a little bit nicer here. So remember, our goal is that we want to go look at the sine function. And what we want to say is, can we pick an interval of values, of x values, over which every single output from sine is achieved, but only once? Because if it's achieved twice, then when we try to work backwards, we don't know which of the 2 outputs we should be choosing. So let's go take a look in Desmos and see what we can see. So I'm going to switch over to Desmos here, and we're going to go ahead and graph the sine function. Now, I'm going to do something to help us visualize this right here, which is that I'm going to make this graph right here be a dashed line because we're not going to keep all of it. We're only going to keep part of it. Right? Again, I can see this issue here that is failing what we called in the last video the horizontal line test. It is not 1-to-1, it's infinity to 1 because horizontal lines will hit our graph an infinite number of times if we go all the way left and all the way right. What we want to do is we want to choose some interval over which we only achieve all of our y values one time. So I'm noticing things like we get y values that go as low as -1. We get y values that get as large as +1. So notice that if we started our interval, for example, at 0 and tried to move to the right, what's going to happen is we're going to get all of our possible positive values from 0 to 1. Those are all y values going from 0 to 1. Zoom in until it gives me 1 right there. From 0 to 1 are achieved. But if we keep going, we're just going to get all of the y values from 0 to 1 a second time. So notice that even this bump right here is unacceptable. Just this bump alone is 2 to 1. There are two instances of every y value that we're getting here. There's two different x values achieving the same y value, and we don't want that to be the case. So it seems like we're not just going to be able to start at 0 and just go to the right for some amount of time, because just going from 0 to pi halves, like I should change my viewing. Oh, that wasn't what I wanted. Let's get rid of these minor grid lines. Let's make our y-axis be more reasonable right here. And let's make our x steps be something that we actually want to see right here, like our pi halves. Okay, now we're looking at a trig graph right here. So again, if we traveled from 0 to pi halves, then we're going to achieve all the positive outputs once. But if we kept on going from pi halves to pi, we're going to get all those same y values a second time, and that's not what we want. But we did get half of all the possible y values, right? The 0 to 1 part. It seems like the other components that we want are the 0 to -1 part. That's the other parts that we want for all the possible y values. I know that the range of the sine function is -1 to +1. I want to experience all those values once, and I'd like to pick the easiest interval over which that occurs. So it seems to me like we could start right here at -pi halves, get all of our negative y values from -pi halves to 0 for x values, then keep going, and as the x value goes from 0 to +pi halves, we'll get from 0 to +1. So every y value has been achieved one time if we look just at this interval from -pi halves to +pi halves. So I think that's exactly where I kind of want to go with this guy right here. So I'm going to graph this again, but I'm going to plop another plot on top of it right here. But here's the thing I'm going to do. I'm going to restrict our domain to the pi halves less than or equal to x is less than or equal to +pi halves. That is the restricted domain that we're going to want to identify for our inverse sine function. So that says we're only keeping this part of it. We're, in a sense, discarding all the infinite stuff to the left and all the infinite stuff to the right, because those are just repeats of all the stuff that we're seeing just in this little interval right here. And so to make this slightly nicer here, boy, I got the runny nose all of a sudden here. Okay, so here is going to be our, man, make this thicker here. No, is that, oh wait, that's the, oh, I see. This is what I want it to be. There we go. So there is our actual interval of interest right there. And you should notice, again, we're getting every y value that sine ever experiences only once. Now, I do want to point out, it's totally possible that we could choose instead, for example, to start at pi halves and go to 3 pi halves. If I did that, boom, there we go. Technically, all the math nerds on earth could have all gotten together and said, listen, guys, here's the way that we're going to define the inverse sine function. Since we get all the values of y one time from pi halves to 3 pi halves, we could choose this to be the restricted domain over which we're going to define the inverse sine function. This just doesn't really make, I don't know, I just want the smallest, easiest numbers I can possibly deal with. Technically speaking, there's an infinite number of choice of interval that we could continue picking out here, where we just go another pi units wide to get all the negatives and all the positives once. We're just saying, let's go ahead and pick the interval that has all the smallest numbers, and in particular, we really like the number 0, so I'm picking the interval that contains 0 right there. So I think that this is our good look at the inverse trig function right here for inverse sine. So I'm going to go ahead and grab this graph right here so we can pop this guy into our notes here. And let's head on back to Microsoft Word and see what we're going to do with this thing here. I'm going to say here, oh man. I'm just not going to write next to it, I guess. I'm not allowed to. Okay. Okay. Just not going to write anything then. So I'm just going to say it. Over the interval from negative pi halves to positive pi halves, we experience every y value one time. That's why we're restricting the domain to only this interval. So to define the sine inverse function, we need to restrict the domain of the original sine function to go from negative infinity. So like sine, right now the domain of sine is negative infinity to positive infinity. We're going to restrict it down to just this one interval that's only pi units wide, negative pi halves to positive pi halves. That's the only place we're actually defining this, right? And let's see why this kind of makes sense on the unit circle, and let's graph each of these things here. So what I'm seeing here is I want to draw kind of three graphs to help me visualize this. On the unit circle, I'm saying I know that sine is a representative of height. So what I want to do on the unit circle is I want to think about on the unit circle, where do we experience every height on the unit circle once? Notice again that I don't want to do things like going from 0 to pi, because then I'll experience all of my positive heights once, and then all of my positive heights a second time. That's exactly what we're trying to avoid. Instead, if we think about going from negative pi halves down here at the bottom, up to positive pi halves here up at the top, then we're having experienced all the y values from negative 1 up to positive 1 once, right? So negative pi halves is down here, up to positive pi halves up there. All the y values, we got them one time. All the sine values have been achieved one time. Right, so there's my unit circle diagram to think about this guy. The other thing that we're seeing here is we're now restricting this sine graph right here to be only these values that, there we go. Hey, not bad. That was actually really good. It's the best graph you're going to get from me today, probably. So there we go. So we're now thinking is that this is our restricted domain sine graph. We're only keeping these parts. Now, what we want to then graph is the graph of sine inverse of x. Now, we know how to graph inverses because we did a whole bunch of them in the last video. We know that to graph an inverse function, we're just swapping the role of x and y. I know that this sine graph normally goes to a height of positive 1 and to a height down here of negative 1. So I'm going to flip this information, right? Now it should be the case that we're going out here. So this point right here is located at pi halves 1. So I want to graph the point 1 comma pi halves on this graph over here. That should now be 1, and this should now be pi halves, right? I'm flipping the role of x and y, and this point that's right here now will be 1 comma pi halves. That's the definition of an inverse. We've swapped the role of x and y. I'm picturing my mirror image over this line y equals x right here. So I can tell since that shape was like, I'm looking at the first quadrant part is like bowed down right here, it should be the inverse of that on the other side. It should be bowed up, right? So we're going to see the shape looking sort of like this. And then coming down here. See, I told you that was the best graph I was going to draw all day here. This point was at negative pi halves, negative 1. So this should be at negative 1, negative pi halves. And real quick, let's just pop over to Desmos and see that that is in fact the case. If I go ask Desmos, what does the y equals sine inverse graph look like? Oh, wait, oh no, I guess it did just, yeah, okay. So it's giving us that shape right there. And there we go. There's our point at 1 pi halves at the very top and at negative 1, negative pi halves down there at the bottom. My graph just didn't have the same proportions for the scaling right here, but we can see that that shape is maintained right there. So here is the entirety of the graph of y equals sine inverse. It doesn't go off forever in any direction. It doesn't go off in the left to right direction because the outputs from the sine function live between negative 1 and 1. And it doesn't go off in the vertical directions to positive and negative infinity because we restricted the inputs of the original function to negative pi halves to pi halves. That's exactly the heights that we're getting to right here. Negative pi halves, positive pi halves for the heights. So we've got our sine inverse function here. Right? We can picture all these things on our graphs now. And by the way, this stuff right here in orange, this is what I kind of visualize when I picture sine inverse. I know that every time I use the sine inverse function, it's always going to be giving me out values that live only on the right half of the unit circle. That's going to be really important here, right? And that's kind of what I'm saying right here. Since we restricted the inputs of the sine function to negative pi halves to pi halves, we know that the inverse sine function will always output values in the range from negative pi halves to pi halves. Remember that domain and range, x values and y values, are going to swap roles when we go from the original function to the inverse. So that's giving me good information. So at the bottom of my screen, this is me yelling at you down here. You will only ever get out values in the span negative pi halves to pi halves when you take the inverse sine of anything. You will never, from an inverse sine function, ever get out any other value outside of this interval right here. This orange span, that is where sine inverse lives and nowhere else. Right? That's kind of our tricky thing to deal with here. So let's look at some easy examples, and then we'll see where this gets a little bit tricky to maintain our status inside of the orange stuff right there. So let's go ahead and evaluate these expressions. The last one we won't be able to get exactly, but we can make a guess and check it in our calculator here. The important thing that I want to do right now, by the way, also, is I want to verbalize what sentence am I saying to myself when I think about each of these guys. So when I think about the sine inverse of 1, here's the thing that I know. Typically, it's the case that when we evaluate our sine functions, right, we think to ourselves things like that our y is really the sine of, and what we know goes into our trig functions is usually angles. Therefore, it should be the case that angles are what we get out when we apply the inverse sine on both sides there. So what I'm thinking to myself is whatever our answer is that's coming out of an inverse trig function is an angle. That's because angles are what go in to regular trig functions, and we have swapped the role of input and output. So angles go into sine, angles come out of sine inverse. So I'm getting out an angle. So the question is, what is the angle that we took the sine of to get 1? So the question again is, what angle would you take the sine of that angle to arrive at a sine value of 1? I know that sine measures height, so I know that I'm interested in the angle associated with a height of 1. How much angle did I just sweep out with my hand right here? It looks like the answer is going to be pi halves right here. So I'll write this one. Right, so this should be equal to pi halves. And notice that we've switched input and output. If sine of pi halves is 1, then sine inverse of 1 is pi halves. Very importantly, notice pi halves absolutely is in our interval of interest because negative pi halves to pi halves is where our answer must be, and we got out the upper edge of our interval right there. Notice importantly that this is defined with that bracket right there, not a parenthesis, meaning those are included in our acceptable outputs. We did land within the orange span right here because we're right at the very edge of our acceptable output span right there. So let's do some more. Sine inverse of 0. I'm saying to you, I took the sine of some angle and I got an answer of 0. What angle did I take the sine of to get 0? Well, since sine is measuring height, I'm asking what angle results in a height of 0? And that's an easy one because that is just 0 radians right there. If we do no rotation whatsoever, our y value is 0. Our x value is 1. So our cosine inverse would be different right here. But our sine inverse of 0 should be 0. Why? Because sine of 0 is 0. So this is one of those ones where you can't really see the switch happen, right? 1 was the input, pi halves was the output. Pi halves was the input, 1 was the output. We switched roles. Here, technically speaking, very technically speaking, this 0 here is actually this 0 over here. We swapped zeros. Obviously, 0 is the same in either case right there. But in this case right here, what angle did we take the sine of to get 0? 0 radians, or 0 degrees you could take the sine of to get a sine of 0. For our next one here, sine inverse of negative 1/2. I took the sine of something, and I got out negative 1/2. What did I take the sine of? Maybe for this one now, we should draw ourselves a little unit circle here, right? So I'm saying I took the sine of something, and the height was negative 1/2. That seems to me to be this angle that we're looking at right down there. I can kind of see where we're going to live. And again, I know it has to be that one because I know that the only possible answers are the stuff on the right half of the unit circle. Sine inverse is always going to output things on the right half of the unit circle every single time with no exceptions, right? So there's technically kind of could have been two answers here. Another way to get that would have been to come over here and get that guy right there, but that's not part of our acceptable outputs from sine inverse. That's not where we restricted the domain of sine to be. So in this case right here, it seems like this 1/2 we know is smaller than root 3 over 2. So I'm going to get the smaller of the two angles. So this should be our pi sixths right here. But notice it's pi sixth rotated downwards in the opposite direction. So I'm going to be getting a negative pi sixths. And again, this is because sine of negative pi sixths equals negative 1/2. Right? Finally, over here, this one isn't going to work out for us. The reason why this one worked out for us is because negative 1/2 is a function, is a value that we've been getting out from our sine evaluations in the previous sections out there. Our 1/2s, our root 3 over 2s, our root 2 over 2s, stuff like that. 1/3 is never something that you got out from sine before. Wow. This couldn't write either of those words right there. Let's try that again. Oh my gosh. Never, never. I'm looking ahead to my next word, gotten. We've never gotten 1/3 as an exact output from sine. So what we need to do is we need to kind of make a guess right here. So what I'm thinking for sine inverse of 1/3 is we're saying I took the sine of some angle and I got a height of positive 1/3. Now I know that if we were to come over here and look at, for example, the height of 1/2, that would be 30 degrees or pi sixth radians. Well, over here we should be getting to even less height than that, right? Our height should only be like 1/3. So this should be me looking at an angle that looks like this, right? This should be my y value is equal to 1/3 right there for my height. I want to guess the angle. And all I can really guess right here is it should be an angle smaller than 30 degrees or smaller than pi sixths because our height is less of 1/3 is less than a height of like 1/2, right? 1/3 is less than a half. So something smaller than 30 degrees or pi sixth radians. So I'm guessing maybe something like 20 degrees or something like that. Let's go ask Desmos what this is. Sine inverse of 1/3. If I come over here to Desmos, I can just do sine inverse of 1/3. And notice it's telling me this decimal amount right there. That's going to be in radians. That's really hard for me to think about. So let's go ahead and convert this into degrees so I can actually see that it's that thing that's like smaller than 30 degrees kind of thing. So I'm going to multiply by 180 and divide by pi. And what do you know? We guessed like 20 degrees and we got 19.47 degrees right there. So we're not going to be able to get exact answers for some of these out here, but you should be able to make some ballpark estimates about what we're getting for sine inverse of some things that aren't otherwise fractions we've seen from sine, cosine, tangent values before, by just drawing a little unit circle, making a little bit of a guess right there. So 20 is a very close guess. I'm going to give myself a check mark right here. And let's say this is approximately equal to 20 degrees right there. This is like a 19.47 or something like that. But our guess of 20 is a very good guess right there. So what we haven't really seen so far, though, is any weirdness come up about this restricted domain. So let's bring that in here now. What we saw in the last section was that the inverse functions are defined by this statement right here. So this looks hairy. Let's talk about this in parts. This says, the first piece says, if you start with an input of x, you then apply the inverse function of f, but then you apply the original function f, it should be the case that since f and f inverse undo each other, it should just leave you with the final output of x. And it shouldn't matter what order you do those things, right? This is like you can either go to the grocery store and then come home. You're in the same place you started. Or if you consider your starting point to be the grocery store, you can go home and then back to the grocery store. And now again, you're back where you started at the grocery store. Either way, those undo each other. So it could also be the case that starting with x, you apply the function f, and then the inverse, f and f inverse cancel, leaving you just with x again. So this is saying, in general, we expect that it doesn't matter which direction we compose these together, the function and its inverse, or the inverse and the function, it should return us back to our original result. But based on our restricted domain, we need to make sure that we end up getting out values that are in the sort of legal span of outputs that we can get here. So notice, in this way that we express this right here, we certainly expect to just get x out from sine inverse of sine of x, because I'm thinking to myself, the inverse sine cancels with the regular sine, leaving us just with the interior output. That was a doing and an undoing, left us back with where we started, x. However, because our final operation was the inverse sine function, it had better be the case that we only get out outputs that are associated with the inverse sine function. And we have decided, very importantly, that the inverse sine function is only going to give us outputs in the span from negative pi halves to pi halves. Unfortunately, there's a little bit of a difference here now. In this case also, I absolutely expect applying sine and sine inverse to x to give me back the exact same x value right here. However, in this case right here, our final operation is the sine operation. So that means to me, whatever I get out as my final x value right here, it has to be one of the outputs that we can get from the sine function. What outputs do we see from the sine function? Well, it goes from -1 to +1. So if we compose them in this order, it's a different type of restriction that we're going to see right here. This is going to go from -1 to +1 because the outermost function is the last thing that we do. And so it is going to sort of be the decider as to what type of outputs are we going to end up experiencing. So let's see how this impacts us. This is now our sort of our tricky examples right here. Right? So sine of sine inverse of 0.5. Right? Now, in this case right here, basically what I'm saying to myself is what I want to say to myself is, oh, we're just going to cancel sine and sine inverse and just get 0.5. We're good. We're done. But I want to stop and double check that that's actually legit. This thing is of the structure that we see right here. And this says to me, listen, since the last thing you're going to do is take the sine of something, it better be that what you're getting out is between -1 and 1. Are you trying to tell me you're going to get out something between -1 and 1 and I see 0.5 in there? Yeah. 0.5 is between -1 and +1. So it seems to me like we're just going to directly get 0.5. That's nice. Notice in our second example right here, we've swapped the order. This is super important. Since we've swapped the order, this had regular sine on the outside, sine inverse on the inside. Now we have sine inverse on the outside and sine on the inside. So now this says to me, listen, I'm thinking to myself, based on my knowledge of inverse functions, that when you compose a function and its inverse, they should essentially cancel, leaving you with the original input, as long as it follows the rules of the restricted domain. Now, does pi eighths fall within the interval pi halves to pi halves? Yes, it does, right? We're recognizing here, remember that and I'm going to draw this picture another time here in a second, in our unit circle right here, the way that I drew this before was saying this is our legal outputs from the sine inverse function, the stuff that's in orange right here, right? So what I'm seeing here in this case is that where's pi eighths? Well, that's a very small angle right there, right? There's my pi eighths angle, right? There's pi eighths. So it seems like because this is part of the acceptable span for sine inverse, yeah, we're essentially just canceling sine inverse of sine and we're getting back pi eighths. And the reason that worked is because pi eighths is in the interval negative pi halves to pi halves. So now let's come down here. Sine inverse of sine of 5 pi eighths. So check this out. I want to say that sine inverse and sine cancel with each other, leaving us with 5 pi eighths, but I know that the sine inverse function is only ever going to give me outputs in the interval negative pi halves to pi halves. Is this in that interval? Well, this is actually 1 pi eighth past pi halves right there, right? 4 pi halves would be pi over 2. That's vertical. This is 5 pi eighths. That is not in our legal span of outputs from the sine inverse function. So very, very importantly here, this is not equal to 5 pi eighths because 5 pi eighths is not in the interval negative pi halves to pi halves. So this is where things get a little bit trickier right here. We got to pay a little bit closer attention. So now I'm saying, well, but does this mean we just can't do it? And I don't think so, because here's the deal. I can totally take the sine of 5 pi eighths, and I know that because the domain of sine really should be everything. I can plug anything I want into sine. But another thing that you're noticing is we've never done anything in terms of pi eighths, so I don't know what sine of 5 pi eighths is. We've done our pi thirds and our pi fourths and our pi sixths. We've never talked about a pi eighths, right? So I don't know what sine of 5 pi eighths is, but I know I'll get some number between negative 1 and 1. And because there's some number between negative 1 and 1, there should be some value that I'm going to get out from sine inverse, because sine inverse spanned negative 1 to 1, or I guess as inputs right there, because sine has outputs from negative 1 to 1. So it should still work out. So here's kind of what I'm seeing to myself. I'm going to draw my very important unit circle picture that goes with this. And by the way, guys, holy cow, do I have to draw myself this picture every single time I think about this stuff. So here's my unit circle, and here's the very important thing that's happening. I'm going to keep on drawing that orange chunk that belongs to the sine inverse function here. This is the span in which it is allowable for me to give my answer for the output from a sine inverse function. My answer has to be on the right-hand side of the unit circle. What we want to come up with is what angle has maybe the same sine value as 5 pi halves, but lives within this interval. So here is 5 pi eighths. What we want to identify is what angle in our acceptable range also has the same sine value as 5 pi eighths. Remember that a sine is a measurement of height. And so it seems to me like there should be another angle that's symmetric to 5 pi eighths that lives within our orange span that would be an acceptable output from the sine inverse function. Where should this be? Well, I know that this is 4 pi eighths up at the top, also known as pi over 2. So it looks like if this one was 1 pi eighth further, this one should be 1 pi eighths previous right here. It looks like 3 pi eighths has the exact same sine value as 5 pi eighths, but it is within our acceptable range of outputs from the sine inverse function. So it looks like we're going to get 3 pi eighths. And the reason that this works is because sine of 5 pi eighths is equal to sine of 3 pi eighths. So notice that it really matters now that we have this ability to identify what angles, plural, are associated with a given output from sine. Right? And again, notice that in this entire time, I never found out what the sine of 3 pi eighths was or 5 pi eighths was. I just know that because they are symmetric over pi halves right here, they had the same angle before and after, that their heights should be the same on the unit circle. So since sine of 3 pi eighths and 5 pi eighths must be the same because they're the same amount of rotation away from pi halves, the heights are going to be the same. And 3 pi eighths is in our acceptable range out from the sine inverse function. These don't just directly cancel to give us 5 pi eighths. It's not an allowable output from sine inverse. This is going to give us 3 pi eighths. Let's go verify this over here in Desmos to make sure that we are not being led astray. So we want to know the sine inverse of sine of 5 pi eighths. So let's do this here. I want to know the sine inverse of sine of 5 pi eighths. And it's giving me an unfortunate decimal right there. I guess what I want to do is that's an unfortunate way to show it right there. Multiplying by pi and 8 and dividing by pi will undo the pi eighths with an 8 piths. And we'll notice it's leaving us with 3 right there to represent that should be 3 pi eighths that we were actually getting out right there. Or maybe slightly easier verification right there. I can just do 3 pi eighths and we can see that that's the exact same number. So Desmos does agree that sine inverse of sine of 5 pi eighths is in fact 3 pi eighths. These didn't just directly cancel because sine inverse can only ever output things on the right-hand side of the unit circle. So we had to identify some angle that shared the same sine value as 5 pi eighths, but lived in our acceptable span of output so that we don't have this confusion between multiple possible answers for any given one question that's out there. Okay? So we're going to play these exact same games now with cosine and with tangent is basically our upcoming thing to do right here, right? So these are the ones that we got to be careful of, but your big thing to remember is that the sine, and I keep on drawing it, this orange diagram is your key to this. The sine inverse function wants to experience every y value once, and so we all collectively as a species of humans have decided, let's define it to always be outputs in the negative pi halves to positive pi halves span, so it will always live on that right-hand side of the unit circle. To now talk about our inverse cosine function, we want to use the exact same concepts, but since cosine is sort of shifted in its location relative to where sine is located graphically, we're going to need to pick a different domain over which we're restricted. Again, our goal is to say we want to experience all possible outputs from cosine once, right? So we're going to switch over to cosine now, but conceptually speaking, we want to do all the exact same stuff right here. And in fact, what I'm going to do is I'm going to cheat ahead a little bit. I'm going to put my Desmos graph of this thing right here, just like I did before. But let's see if we can actually figure this out from the unit circle instead. All right. So here's my unit circle. Now, what I know about cosine that's different than sine, sine measures the vertical location on the unit circle. Cosine measures the horizontal location on the unit circle. So my question to you is, on the unit circle, what span can we restrict ourselves to so that we experience every horizontal location one time? Notice that if we picked the exact same span as we did for sine, the right half over here, that's not going to do it for me because I'm going to get all my x values from 0 to 1 up here. Then I'll get all my x values from 0 to 1 over here again. So not only did I double up on the 0 to 1s, I missed out completely on the negative 1 to all the negatives over here, right? So what I'm kind of seeing here is it seems sensible to me that I want to experience the span from positive 1 all the way to negative 1 to get all the x values one time. That took us all the way from the right to all the way to the left without repeating any of our x values. If we were to keep on going beyond pi, now we're repeating some negatives that we'd already seen up here as far as x values go. That's exactly what we're trying to avoid. Right? So I'm going to, again, kind of label this guy. I'll do this one here in magenta. And it seems to me like a pretty good choice for us to pick right here is instead of the right half of the unit circle for sine, we are picking the right half for sine inverse. We are going to be picking the top half for cosine inverse as to where we are going to insist all of the outputs from sine inverse are going to end up living right here. So this looks like we should be getting from 0 to pi. let's go see in Desmos that that is going to be a sensible choice for us to make using the cosine graph. Right? So popping back over to Desmos here. I want to play this same game up here, but I want to do the cosine function, obviously. So here's our cosine function. And again, I'm noticing that if I were to pick the same intervals we picked for sine, it doesn't do it for me. Here I'm seeing all of my heights once, and then I'm seeing all of my same heights a second time. Excuse me, and I said all of. I'm seeing all of my positive heights once, and then repeating all of those positive heights a second time right there. That's not what I want to be doing. And I shouldn't say heights here because cosine you should be thinking width on the unit circle. Outputs. I got all my positive outputs once, and then I got all my positive outputs again. I never hit the negatives, and I doubled up on the positives. That's no good for us right here. So instead, it seems like if we change this to being from 0 to just pi, then here again, we're going to experience all possible outputs from 1 to -1 exactly one time. So there's none of this repetition, no ambiguity when we try and work backwards, right? And that's the whole thing. The inverse function is the work backwards. We don't want there to be confusion when we work backwards here. So real quick, how did I grab that before? Okay, just grab that again. So same thing. I want to snip this. I'm going to throw this into our, I'm going to have my little Microsoft Word fight again, and we'll, so come back over here into Word. Go ahead and throw that guy in here. And again, the whole point here is we're avoiding repetition of outputs. We wanted to get every y value exactly one time over a convenient interval over which that happens. We like to pick intervals that are, again, we could have picked, instead of from 0 to pi, we could have all chosen that we're going to define the inverse cosine function from 47 pi to 48 pi. And that could be what humanity chose. We just obviously don't want to work with numbers that are out there. So again, we're picking the interval that has 0 in it just because we like the number 0. So this starts at 0, goes to pi. So we will restrict the domain of cosine to be from 0. I have to have a aneurysm over here, Microsoft Word. Let me write without moving my stuff. Oh, buddy. Oh, buddy. How small do you need to be for me to be allowed to write? Didn't move that one. Oh, gosh. Oh, gosh. Okay. We'll restrict the domain of cosine to be 0 to pi. So those are the only values we will ever get out from the inverse cosine function. Again, we are stuck only ever getting out 0 to pi from the inverse cosine function. You will never, ever get out anything that is not on the top half of the unit circle from the inverse cosine function. So there is our unit. We jumped ahead and did that one. We already did the unit circle drawing. We're now going to see here. I just want to scroll up so I can mimic my writing from above right here. So what I write right here, I said, I'm going to write cosine of x over our restricted domain. We know that cosine starts at the top. Right there we are at 0, 1. We know that cosine then is going to decrease down here. It's going to go through pi halves. I know that at pi halves, cosine is 0, so that's going to be pi halves. It's going to get down to a minimum down there, where we are at, looks like at pi, we get down to -1. Therefore, I should be able to draw my inverse cosine function. By mirror imaging this guy over the line y equals x. So it seems like instead of the point 0, 1, I am interested in the point 1, 0. That's now a point on my graph. This point has been reflected over to here. The other thing I want to do is pi -1 should become -1 pi. And this one is very awkward to draw right here. So I guess if that was concave down, this should be It's actually not terrible right there. Let's go ask Desmos to confirm this right here. That was a really weird graph for me to draw right there. Let's go ask Desmos to graph inverse cosine and see that my graph is actually pretty good right there, which is a very big shock to me. And hey, it looks like it is. That's what I drew. Again, my span was my bounds were my proportions of my dimensions were a little bit different right there, but we did get that again. Almost kind of looking like a tangent type curve right there. It's not, but kind of looking like that. And there's our -1 pi, and there's our 1, 0, exactly the same endpoints that we were seeing right there in Microsoft Word. So very cool. Like, yeah, mine's just a squashed version of the correct graph right there. All right, so we've now got our inverse cosine defined right here. So now we can go ahead and look at some examples here. Rather than break these up into the easy chunk and the hard chunk, let's just do them all kind of together right here. So again, we're asking these same types of questions. We're saying things like, I took the cosine of some angle. All right, so we got out 0. What was the angle? This is just asking us to do all of our trig knowledge backwards. If I took the cosine of some angle and got 0, what did I take the cosine of? Since cosine measures left-right amount, I want to know where did we have a 0 for our x value on the unit circle, and that's exactly when we are vertical right here. So it seems like my answer here should be pi halves, and this is because cosine of pi halves is 0, right? We've just flipped our input and our output between our inverse function and our forward direction function right here. Very cool. Cool. Let's look at our next couple right here. We've got 3 others that we want to do. Cosine inverse of cosine of 7 pi twelfths right here. Again, you've never talked about an angle in terms of twelfths. We've done thirds, fourths, we've done sixths, fourths, and thirds, and then our axis angles. We've never done twelfths, just like we'd never done eighths before. So I don't have any kind of like familiarity with this as an angle dealing with my trig functions, but what my intuition tells me is that anytime you compose a function and its inverse, they should cancel given that our domains and ranges all agree. So my question to you is 7 pi twelfths within the legal span of values to be getting out from the final cosine inverse function? And it seems like it is, because I'm thinking to myself, 6 pi twelfths is pi halves. That's our vertical part right here. So 7 pi twelfths should just be a little bit beyond that. That seems to be an acceptable output from cosine inverse. So we're just going to straight up get out 7 pi twelfths. This is what you are hoping is going to happen for all of these compositions of cosine and inverse cosine, sine and inverse sine, tangent and inverse tangent. You're hoping to just cancel the two and just rewrite the exact same number. But it only works that way if the value that is inside the innermost input is in that allowable region associated with the appropriate inverse function right there. And so here we are kind of noticing, again, I'm going to draw my unit circle and say, you know what? It looks like my 7 pi twelfths is right here. And since 7 pi twelfths is in that span, it seems like it is going to just be an acceptable output. So we get to just straight up cancel the function and its inverse and leave ourselves at 7 pi halves. And now you should be looking at our next example and asking yourself the exact same question. Is it the case that negative pi sixths is in our acceptable span of outputs from the inverse cosine function? And it seems like the answer is no. Right? What we have here is we have a negative pi sixths, but what we are only allowed to give as an answer is something that lives in what we've all agreed is the only acceptable region for outputs from the cosine inverse function. So what we have to do is ask ourselves, what other angle has the same cosine value of negative pi sixths, but does live in our magenta region? So we want to come up with an angle that's going to give the same amount of horizontal action on the unit circle, but does live in the magenta region. It seems like here we could choose instead positive pi sixths. I'm putting that plus sign right there to make sure that there's no confusion. We are not getting out the exact same value that's sitting right here because negative pi sixths is not in the acceptable output span for the cosine inverse function. So we identified a different angle, pi sixths, that has the exact same cosine value, but does live within the appropriate region right here. So I hope you are all in agreement that drawing these unit circle diagrams is really, really helpful. All right. And for our last one here, cosine of cosine inverse of 0.9. For this last one right here, you should notice that our outermost function is cosine, not cosine inverse. Cosine, what types of outputs do we ever see here? Well, negative 1 to 1. Is zero point 0.9 in that span? And again, every time you see two functions that are inverses of each other composed together, I'm always thinking to myself, hopefully I can just cancel those two functions because they should undo one another as long as our domains and ranges are all appropriate. And here, zero point 0.9 is absolutely the type of things that I normally get out from cosine. It's in my span from negative 1 to 1, so it seems completely reasonable to me that we're going to just straight up get out 0.9 right there because the outermost function that we were evaluating was cosine, not cosine inverse. So I think we should real quickly go to Desmos and verify these last two. Then we'll talk tangent and we'll call it a day right here. So in Desmos, I want to double check this cosine inverse of cosine of negative pi 6. See that I'm getting positive pi 6. Oop, should switch this over. Cosine inverse of cosine of negative pi sixths. Notice it's giving me a positive number down there. And what is that positive number? Oh my gosh, that positive number is exactly positive pi 6. So Desmos does agree that cosine inverse of cosine of negative pi 6 is in fact positive pi 6 right there because it needs to be within our 0 to pi span. So sine inverse lives here because that goes from negative 1 to 1 for heights. Cosine inverse lives here because it goes from negative 1 to 1 for widths. Okay. The last one that we had right here was our cosine of cosine inverse of 0.9. Oh, and what do you know? It's giving us 0.9 right there. And again, notice our ordering switched right here. Our outermost function determines the allowable span of outputs right there. Our outermost function here was cosine inverse, so we had to agree with the 0 to pi outputs. Here, the cosine function has outputs from negative 1 to 1. 0.9 was part of that, and therefore we did the 0.9. So you should be able to do a power to the negative 1 with a caret symbol, like your 6 on your keyboard right here. Just like I would do x to the power. Oh, yeah, it doesn't show up, but I'm pressing the power button on x right there. So let's go ahead and hit our inverse tangent function here. Hey, the Big Harris. We're doing a trigonometry class right here today. I am not teaching algebra this semester. No, I'm doing trigonometry and a couple calculus classes this semester. So let's hit our inverse tangent here. It's going to follow the same story as sine and cosine. It's going to be a little bit easier to go ahead and find the things that we're interested in here. So let's go ahead and go back to Desmos and let's go ahead and look at our graph of tangent here. So back over here in Desmos, we again want to say to ourselves, we only ever want to get every output once. And so to get every output once from our tangent function, I'm seeing that we're getting our y values out a whole bunch of times, right? We're really failing the vertical line test quite a bit right here. And so what, that's not what I wanted to move. So over here, and I want to move Desmos, there we go. So over here, what I'm thinking to myself is, can we pick an x span where we only ever see all those y values once? It's a little bit more natural of a choice for us to make right here in the tangent situation because we have these asymptotes that create these barriers for us, right? So it looks to me here like a pretty natural choice for me to make is negative pi halves to pi halves. And that's going to give me just one of my spans that I see right here, right? So there we go. There's a nice restricted domain where we do achieve every possible y value, which is literally everything, and we get them all one time right there, right? So, hey, thanks for that, Big Harris. That's nice. So I'm going to go ahead and achieve every single one of my outputs exactly one time right here. And so it looks like this is going to be a nice domain. It's going to actually match our sign information right here. So let's go ahead and grab this guy and come back over into, and actually let me do my thing I was doing before where I do my y equals tangent of x. But then I want to layer over this one on top of it right here. So let's go ahead and make this one our red dashed line, and then make this one our black solid line right here. All right, so there's my one that I'm selecting right here. All right, back over here in Word. One last word fight for the day, and I'm good here. So it looks like here is my region that I have selected for myself. So it looks like tangent, just like for sine, we're going to restrict to being the negative pi halves to pi halves, so that every y value we get exactly one time. So those are the only values we're ever going to get out from the inverse tangent function. Let's go ahead and look at this on the unit circle. And so over here are negative pi halves to pi halves. Now remember over here that the way where we talked about visualizing the value of tangent on the unit circle was by saying what's the height of the stick that we would draw on this vertical line at x equals 1 if we were to open up some given amount of angle out here. So notice my heights that I would achieve out here. I can get all my positive heights out here by checking out all of my angles from 0 to pi halves. I can also get all of my negative heights on this vertical line out here by going from 0 to negative pi halves. And that's why we're going to be getting our span right here. That's going to match from negative pi halves to positive pi halves. There we go. So again, that's going to be our span of interest for us right here. When we go to graph just our one period of tangent, those are our asymptotes. Ooh, notice one small difference that I made a tiny mistake here, by the way. A tiny mistake here. Again, importantly, there's no repeat parts out here, right? Tangent just keeps on doing copies of that in general, but we're restricting the domain to only see one copy of the tangent function, right? No repeats out here. Now, notice one thing though. My one mistake that I made right here is brackets. This should really be parentheses right here. And the reason that's the case is because I can't ever get out the value of negative pi halves from inverse tangent because I'm never allowed to plug in the value of pi halves into regular tangent. That would be giving us our undefined location. That would be where we get that division by 0 and we do sine over cosine right there. So importantly right there, we need to make sure that we are not including that negative pi halves and pi halves as individual points right there because those aren't in the domain in the first place right there. Cool. So all we got to do now is just graph our inverse tangent function. and our y equals tan inverse of x. Now, this one's going to look a little bit different, and this one is actually a pretty important function. This one's actually used kind of for a lot of things, this inverse tangent function right here. Notice that this guy has vertical asymptotes at negative pi halves and positive pi halves. Therefore, our inverse function should have horizontal asymptotes at negative pi halves and pi halves. Because we're switching our x and our y stuff, right? This guy looks like when I do positive x's, I get positive y's, so I expect to have that same type of shape out here. So we're going to, and negative x's gives us the negative y's, so we're going to get a shape that's going to look like this guy right here. And it's going to go off forever to the left and forever to the right, but its outputs are stuck between negative pi halves and positive pi halves right here. We should go verify that because that's a clunky looking graph right there. Let's go take a peek in Desmos super quick, and then we'll do a couple, we'll call it a day. So there we, let's see, x, and if I turn these guys off right here, yeah, it looks like we're getting that same tangent graph, but it's stuck. Like it never goes above and below that pi halves and negative pi halves. In fact, if we wanted to, we could even do things like say x equals pi over 2. Oops, I meant to say y equals pi over 2. And you can see that that is going to be that bounding line for that tangent inverse function. It's never going to cross over that. Similarly for the negative pi halves that are down there, right? So we know where that tangent stuff's going to live. Let's go see if we can make this guy happen right here. Let's do a couple examples, and I think we'll be good to go. Uh-oh, I know what I did. Wow. All right, I do want to move this stuff, but I know that that word example is going to, yep, that's what I thought. Oh, there we go. All right, let's go ahead and evaluate these following inverse trig expressions. So tangent, always a little bit tougher than our sines and our cosines here. So tangent inverse of 1. I'm saying to myself, I want to know what angle did I take the tangent of to get 1? Well, there's two different angles I can think of in the first in our first unit circle, but we're only keeping half the unit circle as possible outputs associated with the tangent function. So I'm seeing here, I took the tangent of some angle and got out 1. What was the angle? Well, I know that tangent is sine over cosine, and so sine over cosine must be equal to each other. If we got 1, right, their ratio must be 1, meaning that they're equal to each other. And so it seems to me like we must have equal sines and cosines, so equal x stuff and y stuff. We know that's associated with our 45-degree angles, or pi fourths right here. Right? My unit circle, seeing it right here, and there we are, right there at pi fourths. And we know that that is within our legal span that we have selected for tangent. Right? Tangent was supposed to live there. We got something that's right there. And again, I want to point out that like there's actually another one. Technically down here, you could take the tangent of not 1 pi fourths, but 1, 2, 3, 4, 5 pi fourths. Tangent of 5 pi fourths is also 1, but you're never going to give me 5 pi fourths as the answer because 5 pi fourths does not live in our acceptable output span right here. Right? Very similarly, for tangent inverse of negative 1, same deal, same exact deal actually. I want to be picturing that we're getting out the tangent being negative 1. Well, there's two places where that happens. One of them's right there, but that's not going to be in my legal span. The other one is going to be over here where the sine and cosine values are equal, but one of them's positive and one of them's negative. So that's actually going to be the one that I want right there, not this one, because that is not in our legal output span that we've agreed upon for inverse tangent. Right? It's got to be one of the angles that's in this region that we've agreed upon here. Right? So it looks to me like my answer here. And also another thing I want to point out right here, you could totally call this angle here what? 1, 2, 3, 4, 5, 6, 7 pi fourths. This sort of is 7 pi fourths, except 7 pi fourths is not in my negative pi halves to pi halves. I have to reference this angle as being negative pi fourths, not 7 pi fourths. 7 pi fourths is not in the span negative pi halves to pi halves. You've got to be in there. And for our last one here, tangent inverse of negative 1 over root 3. This one's a little bit tougher because I'm always a little bit uncomfortable with my tangent values versus my sine and cosine values here. But again, I'm going to draw my unit circle. I'm going to think about where my allowable outputs are. Whenever I see these negatives here, I know that's got to be my fourth quadrant stuff, my stuff on the bottom half. This is going to be all my positive tangents. This is going to be all my negative tangents over here. The thing that I'm recognizing is that the square root of 3 is a number bigger than 1. So when I draw this, it's got to be something that's doing something like this, right? Where this height right here is negative root 3. So this looks to me, I know that that's one of my like 30s or 60s. It looks like that's got to be the 60 right there, or negative pi thirds, right? Because it's got to be the height that's longer than 1, so it extends beyond the unit circle. The other one that we get is like root 3 over 3, which is smaller than 1. That would be giving us our negative pi sixth right there. That one I feel like is worth a little double check over here in Desmos. Let's go verify that tangent inverse of negative root 3 is in fact negative pi over 3. Then we'll do one last problem and call it a day right here, kind of looking forward to where we're going to be here. So I want to check this guy out. Tangent inverse of negative root 3. And what is it giving me here? Negative pi over 3 to check. Oh, yep, these two decimal values are exactly matching right here. So Desmos agrees that tangent inverse of negative root 3 is in fact negative pi thirds right there. Cool. So what you've got to really remember here is where are these legal spans for each of them, right? Kind of part of your mission here with this stuff now is to remember, and I tried to use my colors to guide us along here, that for sine, we're always keeping the right half because we'll experience every vertical height on the unit circle once from bottom to top. For cosine, we did the magenta stuff because we want to experience every width from left to right once. That's from 0 to pi. Tangent, since it's going to be these heights of the triangles that are touching this line x equals 1, we'll get all of our negatives down here and once, and we'll get all of our positives up here once. If we did this stuff right here, we get all of our positives once, and then, okay, so I guess, but we would cross over that pi halves and it'd be missing. Technically, actually, we could have chosen this, but we would have had a hole right there, which is why we don't really like that one. And so we just chose our one period of tangent, the middle one right there, and that was good for us right there. So we've got to remember those. So where are we going with this? Our goal is to be able to solve trig equations, right? This is going to be one of our big goals this section. It's not going to be till like section 7.5 that we're going to talk about this one, but recognize that we can do this guy right now. So let's do this one real quick and we'll kind of call it a day right here. I want to solve this trig equation, and we straight up know how to do it now. My first step, I think I want to subtract 1 from both sides. Next step, I want to divide both sides by 10. It's negative 5 over 10, also known as negative 1/2. Now I would like to apply the sine inverse function to both sides. So what this should now lead me to is a statement that says 2x is equal to the sine inverse of negative 1/2. So now I got to say to myself, okay, on my unit circle, I know that the sine inverse function is defined so that we get out all of our sine values once. Sine is measuring height, so I'm remembering here that this should be all of my heights one time from negative 1 to 1. So this should be these guys out here. I know I want to get out from the sine function negative 1/2 from one of those angles right there. What is that angle going to be? That should be our negative pi sixths. So it looks like we're going to get 2x is negative pi sixths. And then over here, I'm going to get x equals, now we can divide both sides by 2. That should be giving us negative pi twelfths now is what I'm claiming our answer is. Let's go verify this in Desmos, and we will just read one sentence and call it a day right here. So I want to throw this entire sentence into Desmos. 10 sine of 2x plus 1 equals negative 4. 10 sine of 2x plus 1 equals negative 4. And notice it's giving me just an absolute ton of answers right here. I am interested in an answer that exists. It's not going to let me like, oh, that's kind of dumb. Here, let's do this. Let's do this. There we go. Now it's now I want to do 4. It's 4 right there. And we can look to see where do these intersect one another. And what I'm going to see right here is I'm going to see some intersection locations right here. Oh, equals negative 4. I was like, that's not the right thing. I want to see the intersection of the graphs y equals 10 sine x and y equals negative 4. And so I'm going to scroll down now to my, oh my gosh, scroll with me, Desmos, down here. And what are we getting? It's telling me the answer. Oh, what do you know? Negative pi twelfths is exactly where those two things are the same as each other. Where this expression is the same as this expression is when x is negative pi twelfths. So Desmos absolutely agrees with that little bit of algebra and trigonometry that we just collectively did here. So this takes a little bit more kind of like thought and effort and stuff like that. But the point is, we're going to be covering this. This is going to be 2 sections of the textbook are going to cover all of our solving trig equations right here. But we'll be hitting that. I think it's section 7.5 and 7.6 in the textbook, or even 7.6 and 7.7. Anyway, it's the end of our chapter 7 section where we're actually going to finally get to our solving equations. And the reason is we're going to want to have a little bit more help with manipulating trigonometric equations first. So we're actually going to be covering a few sections of trigonometric identities. So next week, we're going to hit 7.2. In 7.2, we're going to look at how do we compose trig functions and inverses where they're not the same function, right? How do we compose a cosine with a sine inverse, stuff like that. So that's what we're going to talk about next week in 7.2. Then in 7.3, 7.4, 7.5, I think it is, we're going to look at trig identities. That is a trig expression that's represented as a different trig expression. And then I think it's 7.6, 7.7, we get our equation solving, and that's our bulk of chapter 7 right there. So there we go. I'm going to wrap it up here for the day. This ends our week 5 stuff right here. We did inverses and then inverse trig functions right here. Heavily dependent on our information in 5.4 to understand these restricted domain concepts right here, which is why we had to go back and cover that this week. So we'll pick it up with 7.2 with more on inverse trig. So next week our goal is to get into solving stuff like this. And all we're going to have to do is draw a whole bunch of triangles for ourselves. Just be a little bit careful with a little bit of triangle drawn out here, and we'll be able to knock these guys out. So I will see you guys next week for 7.2. Have a good one.